Hello everyone, I'm pleased to announce my new tour for 2024. Beginning in early February and running through June, Tammy and I and an assortment of special guests are going to visit 51 cities in the US. You can find out more information about this on my website, jordanbpeterson.com, as well as accessing all relevant ticketing information. I'm going to use the tour to walk through some of the ideas I've been working on in my forthcoming book, out November 2024, We Who Wrestle with God. I'm looking forward to this. I'm thrilled to be able to do it again, and I'll be pleased to see all of you again soon. Bye-bye.
It is like the holy grail of fusion of energy, the things in this. Why? It's because it actually uses very few raw materials to build the thing, if you build it effectively. And the fundamental fuel source is essentially inexhaustible on Earth and freely available to everyone. It's like that's why you pursue it.
Hello, everyone. I had the privilege today to speak with Dr. Dennis Whyte, who, like me, is a denizen of a small town in Western Canada, a small prairie town. Be that as it may, he's also one of the world's foremost authorities on nuclear fission and has been at the spearhead of both technical and commercial projects to make fusion technology a reality. And fusion offers the opportunity, essentially, if it can be mastered, of unlimited energy and potentially at a low cost. So it's the ultimate in transformative technologies. We talked about the fact, too, that the fusion revolution, which has been promised, let's say, for decades, which isn't that long a time frame, all things considered, is now being facilitated by tremendous advances in materials technology and computational technology, and that just last year, there was one variant of fusion technology that produced for the first time more energy than it consumed, which is a milestone on the pathway towards true commercial viability. And so we talk a lot about exactly what fusion energy is, how it differs from standard nuclear energy, where we are in the process to transitioning, let's say, to the kind of future that would be endless clean energy at an extraordinarily low price, right? And that really brings with it the possibility of lifting all the remaining poor people in the world out of poverty if we could just get that right. So it's a fairly technical discussion. It'll be very appealing to you engineering and science types, but for everybody who's interested in the issue of energy more broadly and the science fiction reality that the world is about to become, then follow along with us. So thank you very much, Dr. Whyte, for agreeing to talk to me today. We might as well jump right in. I think the thing we could do for our viewers and listeners that would be most useful to begin with is for you to tell them what fusion energy is and how that differs from standard nuclear energy, just like a rationale for the pursuit of fusion energy and a place and placing of it in the proper context with regard to our pursuit of advanced energy and reliable energy supplies.
Right. So fusion is the process of fusing together the most abundant and the lightest element, hydrogen, into heavier elements. So it actually changes the element. And this is the process that powers the universe because it powers all stars, including our own sun. And you can think of a star, our own sun, it's a big conversion factory. It's like a standard burner in the sense that it takes the huge masses of hydrogen that the sun is made out of, and in the center of it, where the conditions meet the requirement for fusion, it converts the hydrogen into helium, and by that process, releases staggering amounts of energy per reaction. Usually when I comment in public about fusion, it's like, so fusion makes life possible in the universe because it's the radiant heat that comes from stars that makes life possible on a place like the planet Earth. So it is you think of it, it's the quintessential or fundamental energy source of the universe. That's the starting point. So it distinguishes, why is it such an effective energy source? It's because it changes the element, right? So what happens is that if you take the mass of those starting particles of this before you fuse them together, they have larger mass than the particles that result from this. And you go, but how can that be? Because we all learned in school that, mass cannot be destroyed or created. But this is what Einstein realized, was that in fact mass and energy are the same thing. And then when you convert them in these processes, you end up with energy. And it's hard to imagine how much of a different process this is than either fission or standard chemical reactions, which is basically what we run the world on today. And in terms of comparing it to chemical energy, the average energy released per reaction or per mass of particle is about 10 million times larger. It's amazing, right? So this is why stars on our own sun can last for 10 billion years. I mean, there's an enormous amount of hydrogen in the sun, but if it was running on a chemical process, like burning hydrogen, like you would think of in a fuel cell or something like that, it would only last for a few thousand years. It lasts for 10 billion years. That's the difference between them. And with respect to fission, it's actually, there's a relation there in the sense that fission changes the elements as well too, but it's literally the opposite process. Fission, as the name implies, splits apart or fissions the most unstable, heaviest elements that exist, like uranium. And again, by this equivalent of energy and mass, it releases energy, but it's a completely different physical process. And then we can discuss a little bit more about what that means, but that at the starting point, you can say, the universe already voted. Fusion is the energy source of the universe. Just the question is, how do you actually harness it on Earth? And the consequences of harnessing it are very different than either chemical or fossil fuel energy or standard nuclear energy.
Now, you said that it's in the deeper reaches of the sun that the fusion reactions take place, and the sun is extraordinarily large, and the conditions there are very much unlike the conditions on Earth. So what are the conditions under which fusion becomes possible, let's say, on the cosmic landscape? And then how is it that those might be duplicated? How is it even possible to duplicate those on Earth? And also, how is it possible to duplicate them on Earth without things going dreadfully wrong?
Right. Yeah. So the conditions in the set. So I'll take it varies from star to star. Actually, there's nuances to the differences in different types of stars, but I'll take our own sun as the example. It's the easiest one. So as you imagine, like in the center of the Earth, like we learned this in elementary school, like there's different layers to the Earth, right? You have an outer cold crust, and as you get towards the center, because of the pressure exerted by gravity, and the core and the mantle, these are all higher temperature, and they're much denser because they're under so much pressure. The same thing happens in the sun, which is actually larger, much larger than the Earth. And what you can think of is as you go from the surface of the sun, which has got is in contact with outer space, that has minimum pressure, and it's actually the coldest part of the sun. It's at around 5,000 degrees. And as you start going towards the center of the sun, the temperature keeps increasing, the pressure keeps increasing. And eventually, when you reach the center of the sun, it's approximately 20 million degrees Celsius in the center of the sun. It's under those conditions that basically the fusion reaction can start to occur in significant quantities. And that's what's required for a star to essentially ignite, is that there is sufficient conditions of particularly temperature and pressure that allow enough fusion reactions to occur that it starts to keep itself hot to allow other fusion reactions to occur. So this is interesting, is that there are entities, even our own solar system, which didn't quite make it to stars. So there's actually an Arthur C. Which one was it? I think 2010, right? Arthur C. Clarke, brilliant scientist and writer, postulated that at the end of that story, you might remember that Jupiter is turned by the aliens into another sun in our solar system. That's not quite totally possible, but it is interesting. Jupiter basically has a very similar composition to the sun. It just didn't get quite big enough and hot enough in the center to start triggering enough fusion reactions to make it a star. So what this means is that fusion occurs naturally only really in one place in the universe, and that is in the center of stars, because that's the place where you can get the conditions of a particularly temperature that allow it to remain hot enough to be able to sustain the fusion reactions. And quickly, like why is that needed? It's because this process of pulling the hydrogen, pushing them together to fuse, means that you have to overcome extraordinarily large forces which don't want them to get close to each other, which is a basic force of nature. So it's the electromagnetic force, because the electrical repulsion between those two particles doesn't want them to come together. So you have to have high average energy to essentially overcome that barrier and get them to fuse. So you can think of, like, we use analogies like you have to have your match or your kindling hot enough to get the big fire started. Well, in this case, you sort of have to get enough average temperature or energy to start up the reaction and to get it going. So those are the requirements. So this comments then as to why we could imagine that you could make this happen on Earth is the requirement here is actually not so much around the energy, because for almost 100 years, we've actually induced fusion reactions on Earth with particle accelerators. This is one of the first things that was discovered, actually, when particle accelerators were developed in the 1930s. The question is about how you maintain the temperature of this medium, of the hydrogen fuel, that allows it to stay hot enough for it to keep fusing. And the sun and stars work by the fact that how is it allowed that the center of the sun is so much hotter, 20 million degrees? Then how can it not this heat escape? Well, it does escape with finite probability or time scales, but are very long time scales, like orders of 1 million years or something like this. And the reason this is happening is because it's the sun's own gravity, which is containing this hot core, which disallows it to escape and dissipate and therefore cool down and then stop the fusion reactions from occurring. So this is why as it turns out, gravity is the weakest of the fundamental forces by a lot, like many, many orders of magnitude. And so for this reason, in order for fusion to be viable on Earth, you can't do it by the exact same process that a star works, because it takes something the size of a star. So with a few exotic sort of examples like neutron stars, this is why stars are actually enormously large, because gravity is a very weak force. So this ironically, in some sense, it comes back to what I just commented to. The thing that makes fusion hard is this electrostatic repulsion that is occurring because the two like-charged particles, they both have positive charge, don't want to get close together to fuse. We actually use its cousin, which is the magnetic force, is one of the ways to do this. We replace that gravitational force, which is something which has much higher effectiveness than gravity. And primarily what we use is the electromagnetic force. And so that's what we, in fact, primarily use on Earth. Although it's not exclusively that, it's mostly that's the thing that we use, to sort of recreate these temperatures, particularly that occur in the interior of the sun. So,
Okay.
So I think your last question was why isn't that crazy? Like, it seems dangerous for something to have something at such high temperatures on Earth. It's actually the opposite of that. And it comes from a little bit of a subtlety of understanding the thermal balance in a fusion system, is that while the materials, this fuel gets extraordinarily hot, there's extremely little of the fuel, like very, very little of the fuel. So one of the leading concepts, for example, that's the focus of my own research in magnetic confinement, the energy content of the fuel, even though it's at 100 million degrees, is less than boiling water. Because there's so few particles in it. So you actually you basically need, in order to have something that has high energy content and therefore could be considered dangerous, it has to have high temperature and large numbers of particles of it. So fusion has very high temperature, but very, very few particles. So when you put those numbers together, it turns out it's not dangerous at all. And the other thing that makes it safe is because what makes fusion hard on Earth is, in fact, isolating it from anything that is terrestrial. anything that's Earth-like, anything that has root temperatures, anything close to what we're used to, is that what tends to happen is this fuel will just leak its heat so fast into that medium, it cools down and immediately stops making fusion. So, in fact, fusion has inherent safety built into the physics of it. It's actually not really a engineering safety concern. You can't actually, in many ways, you can't actually use it intentionally to do bad things with it because of those physical properties of the fuel.
Okay, so let me see if I've got this straight so far. So a star aggregates together, primarily hydrogen, because of gravity. And if there's enough aggregated together, the gravitational density, especially in lower levels of the star, becomes such that fusion reactions can begin to take place. Now, is that primarily because initially is it that the atoms are crushed together despite their electromagnetic opposition? They're crushed together by the pressure that's a secondary consequence of the gravity. So they're just brought into proximity. And and what happens? Does like one fusion reaction take place and then start a chain reaction under the appropriate conditions?
Yeah. So no, actually, which is the other part of. Thanks for asking that. That's a very insightful question. Actually, it doesn't work through a chain reaction. It works rather through a thermal process, which is different. Let me just quickly explain this, because this is a fundamental difference to fission. So in fission, what happens? You imagine. So here's your great big uranium nucleus, right? And the fission gets triggered by an extremely simple process in many ways. It's a neutron, which is one of the components of the nucleus, which is made of neutrons and protons. Neutrons have no electric charge, protons have electric charge. They hold themselves together in the nucleus through the strong nuclear force. A neutron, which can participate in that force, basically gets in proximity to the uranium nucleus, and it splits apart and releases energy. It also releases neutrons when it does that. And so when those neutrons leave that as a cause of that reaction, if you design the assembly of the uranium in that case, or other materials which can undergo fission, what you do is you design it such that it's that particle that actually starts the next reaction. So in a power plant, like in a fission, nuclear power plant, you design this very carefully and control it very carefully, that on average, when one fission reaction occurs, one particle that is released from that triggers the next fission reaction, and you control that. If you intentionally don't control that, then the process runs away, because that one, say, triggers 2 more fission reactions, and then 4, 8, 16, and up it goes, and in fact, that creates an explosion. Fusion does not work that way because the products that are made by fusion are very, very hard to fuse. They actually don't trigger the next fusion reaction. So in fact, that almost comes by definition, because what's happening is primarily it's converting the fuel into helium, and helium is an extremely stable nucleus. It actually doesn't want to fuse anymore. That's actually why fusion is such a good process and such an energy efficient process. So it's not that particle that wants to fuse anymore. It's the heat which is released from the fusion reaction that gets the fuel a little bit hotter. If you get it a little bit hotter, then that will want to make more fusion reactions. And as it releases heat, it'll actually get the fuel hotter and it will go up.
Why is it more likely we talked about the relationship between gravitational pressure and the preconditions for fusion. Why is that more likely at higher levels of temperature?
Right. So that does come from the fundamentals of the process. So if you take a single reaction of fusion and you consider the average energy of the particles, that in general, although there's a limit to it, as you increase the average energy, the velocity, essentially, the particles to fuse, that gives them a higher likelihood of overcoming the repulsion.
Because they're in motion.
And then basically allows them to do that. And that's a good one to speak about, because as I commented before, accelerators, in fact, I have an accelerator run by graduate students at MIT that can trigger fusion reactions all day long, because you take an accelerator, you give a single particles back basically a high average energy, and you impinge them onto a target that's of appropriate composition, you'll trigger these kinds of fusion reactions all day long. That cannot make net energy. It turns out it's because what's happening is that basically most of the energy that you're supplying to this particle just gets lost in useless heat, essentially, in the system. What's happening inside of stars, and that's why I said temperature, not energy, is that it's a contained thermal system. What I mean by thermal, this means it's the equivalent, that we're used to of thinking about, like we think of water of having a temperature or air of having a temperature. This medium, which is called a plasma, actually has a temperature. It is a system in which the particles have a distributions of energies based on thermodynamics. And so that's why I call it a temperature. So this is key. It's a thermodynamic process in that sense, is that you have something inside of it, is that individual particle reaction releases kinetic energy, but because that's forced to give that energy back as heat into the medium, the temperature increases, the average energy of the particles in the medium increases the probability, and this builds up your way to actually to being able to do that.
So you crush them together, and that increases the probability of fusion to some degree, and then you heat them up, and that increases the probability even further. So I'm curious about the temperature and the movement of the hydrogen atoms. So this is a stupid question, likely, but the answer doesn't spring to mind. As you increase the average temperature of the plasma, what actually is happening to the atoms? Like, are they vibrating back and forth faster? And if they're vibrating back and forth faster, why don't they just go off in a single direction? Why is the motion like that? I can't understand that exactly, because you'd think that with a given momentum, they would go in a specific direction. Are they bumping into other atoms? Is that the issue?
Yeah. So, right. So now I have to pull up a whole other level about what the medium of the fuel is. And it's because, so the temperatures involved always in fusion exceed tens of millions of degrees. So it turns out that any matter, when you increase it up to around 5 or 10,000 degrees Celsius, it turns into a different phase of matter. So you can no longer think of it as atoms in a lattice as you do in solids, or atoms floating, basically a fluid like water, or even the atoms in this air bumping into each other. It turns into a completely different phase of matter. This is called a plasma. And plasmas have unique properties because what they're doing is disintegrating the atom. And atoms are made up of, the simplest one is hydrogen. There's a positive charge nucleus. In the case of simple hydrogen, it's just a single proton. And things like deuterium, which is the heavy form of hydrogen, there's a proton and a neutron that are held together. And then there's a single electron, a negatively charged electron around it. So all the matter that we always deal with on Earth, solid, liquid, gas, are all in the phase of they're all stable atoms that are holding themselves together through the atomic forces which are in there, not nuclear forces, which is interesting, atomic forces which are in there. Once you get up above 5 or 10,000 degrees, those temperatures are so high they start breaking those bonds, and basically what happens is that there's enough energy that on average, the electrons are all pulled away from their partner that they had here. So the distinguishing feature of a plasma is that, in fact, they're not little atoms like wiggling around like this. They're actually freely going around particles that all have electric charge. And particularly when you reach temperatures required for fusion, everything has a charge in it as well, too. The reason this is... So, by the way, plasma is a discipline in and of itself. I actually work at a place called the Plasma Science and Fusion Center. Plasma is the central medium that you use to make fusion happen. So, like, what is an example of that? Well, it's the sun. The sun is not actually a ball. We think of the sun as a ball. Oh, it's a ball of maybe gas or liquid or something. No, it's plasma, because everything is above 5,000 degrees in the sun. So this gets a little bit harder to say. So what does this mean about that it's a plasma? Like, why is it special? Why is it difficult to think about? This does go into your question, but how on earth do you actually tame this, right? Well, what happens, and from this, it goes back to this whole pushing against each other through the electromagnetic forces, and particularly the fact that they've got charges now. Remember, I told you before, when the hydrogen protons come together, they don't want to come together too close because they get repulsed from each other. That's actually a force that acts not when the particles physically touch one another, but is always present because they're interacting through their charges. So particles out here, like they can be zipping by each other like this, but actually impact each other because they begin to interact with each other through a basic force of nature, which is again the electrostatic force. And it turns out, well, it's sort of intuitively almost, and this is why by the way, plasmas are not intuitive, because the physics that dictates them is action at a distance, and therefore they have a really pretty wild set of collective behaviors that has been a source of study it's an entire discipline of physics, plasma physics, that has been studied for over 100 years to sort of understand this medium. But in the end, one of the ways we do describe it is you can almost think of like a gas, but rather the particles have charge, and so they're bouncing off each other without actually physically touching into each other, which gives them complex sets of behavior. So in the end, in order to contain this, like in the sun, that's happening in the sun, is that this means that there's sort of randomized motion actually for any individual particle.
Right.
As an ensemble, they actually have predictive ways through statistics, statistical mechanical descriptions that allow us, like we do in gases and solids and others, that we can sort of describe this in terms of a thermodynamic point of view, even though it's in this crazy plasma state.
We're experiencing a lot of global instability as we plunge into primary season. How are you protecting your family in the midst of all this chaos? The fact is, there is one asset that has withstood famine, wars, and political and economic upheaval dating back to biblical times, and that's gold. It's not too late to diversify an old IRA or 401k into gold, and Birch Gold Group can help you with that. Birch Gold can help you create a well-thought-out and balanced investment strategy. They'll help you convert an existing IRA or 401k into an IRA in gold without paying a penny out of pocket. Diversify into gold today. Just text Jordan to 989898 for a free info kit. With an A+ rating with the Better Business Bureau, countless 5-star reviews, and thousands of happy customers, I encourage you to check out Birch Gold today. Text Jordan to 989898. Claim your free info kit and protect your savings with gold. That's Jordan to 989898.
So it sounds, let me use an awkward analogy maybe, it sounds like a bunch of singular north poles of magnets trying to get along together in a crowded room.
Yes.
Is that approximately right? Because you can imagine pushing north poles together. They don't like to come together. They twist around each other, and you can imagine that being compressed together as a consequence of gravitational force. Now, would it be then that there's a probability distribution that those interacting particles are going to actually collide hard enough to fuse? So they're interacting, and now and then the interaction is such that they fuse, and there's some set probability of that increases as temperature and pressure increases.
That's exactly what it is. So it's, and in the end, what happens is you can take this statistical approach to the large distribution of particles that are behaving in. You can't predict an individual particle's probability.
Right.
But an enormous ensemble of them, you can start treating them statistically, and that's in fact exactly what we do. We use laboratory measurements of things like, we basically take single particles and find out their probability of interacting at a given energy. We measure those extremely accurately. And then what we do is we assume that the system is in this deep thermal state. Essentially what's happened is it's maximized its entropy effectively because they bounced off each other so many times. And then you can statistically describe a probability that actually the particles will fuse. And this probability depends only on the temperature. We call this a rate coefficient to be more technical, but that's okay. It's basically just the probability in an ensemble of these particles that in fact the fusion can occur because of these interactions.
Right, and the denser that medium, the higher the probability that those are going to occur.
So, and then we tend to separate those. There's basically one function, and this is key actually in fusion, which we might get a little bit more into, is that So one of the independent, we consider the independent parameter or the controlling parameter primarily temperature, because it is an absolute requirement. So if you take the most simple fusion reaction, there's minimum temperatures that you can get net energy out of it. It tends to be around for the terrestrial sources. So it's about 45 million degrees Celsius. That depends only on the temperature. So we tend to break it out. There's one part of the reactivity depends on the temperature, and then we separate, and there's another one that depends on the density of the fuel. And this is actually intuitive, right? It's like as I increase the density of the fuel and I have fixed probability for an average ensemble of them, I can calculate how many fusion reactions I'll make in that medium in a unit of time and in a fixed volume. So this is really important because this informs us about how much for a terrestrial energy source, how much fusion power, because every time a fusion reaction occurs, it releases energy. So we can actually calculate from this directly the amount of power that we make in a fixed volume of this fuel once we reach those conditions. And it depends on the density of the fuel and the temperature of the fuel. Yeah.
Okay. So now we've explained how this occurs in the sun. We've explained why it isn't a runaway process. We've described the relationship between pressure and temperature, but then we're stuck with the next mystery, which is, well, you don't have the sun on Earth. You don't have that gravitational pressure, that volume of hydrogen. How do you duplicate the conditions that are necessary to produce fusion? How do you produce temperatures approximating, you said 45 million degrees? It's an unimaginable temperature. It's no wonder that things cool down when a fusion reaction would cool down if it touches anything earthly, because that would be like plunging it into the most frigid deep freeze imaginable. So how do you duplicate these conditions, however temporarily on Earth? You do something like make these electromagnetic containers, and I know that you use laser beams to increase the density, but maybe you can walk us through the construction of the electromagnetic container, what technical innovations that's dependent on, and then how you attain those temperatures and pressures.
Right. So I've introduced the two of the three requirements for fusion. So one is the temperature, the other one is the density of the fuel. The third one is before I talk about the technology, I'll just describe what it means conceptually. So we call this confinement. What I mean by confinement is that because these systems must be thermalized, and that namely the fuel must have a temperature, technically what that means is what I've actually allowed to happen is that the fuel medium is having way more interactions with themselves that don't fuse. It's just like thinking about the particles in this room colliding off each other. All those things, what they do is they exchange energy and momentum, and that's actually what allows the system to thermalize. And once in a blue moon, a fusion reaction will basically happen. So that's what's going on. So what that means is that you must have a system that provides particle and energy containment. What I mean by this is that it's okay because this fuel is isolated in some way away from everything else, so that you basically allow those non-fusing reactions to occur, and you don't really care because you've provided containment. So what does this mean conceptually? It's like of whatever you think of your fuel assembly on this is that there's some physical mechanism which is disallowing it to basically touch anything that's at room temperature or even close to it. So it's isolating it in some way. Okay. So that's the concept. So we call this the energy confinement time. And the way that you can think of it, you just sort of close your eyes, imagine you got some ensemble, and you put some unit of energy into this, and you kind of wait, and you say, oh, it took this long to cool. That characteristic time is called the energy confinement time. This was conceived of by a scientist in the 1950s, Lawson, who realized added this important concept into play. So it turns out that when you look at a fusion system, is that once you reach a certain temperature, it's actually, and it takes a little bit of math, but it's like whatever. It's pretty much the first thing you teach, like entering grad students at MIT about how to establish fusion energy system, is that it requires a minimum amount of containment for a given amount of how many fusion reactions you're making, and that's set by the density, because you've assumed some kind of temperature in it. And it turns out when you work through the math of it, it's the product of the density of the fuel and this energy confinement time that actually realize what you want, which is to get net energy out of the system, and particularly the ultimate goal, which is you basically put in almost no external energy, and the whole thing is just keeping itself hot by its own fusion reactions. So it's very important. And the story that's a little bit complicated, but it's so important to understand in fusion, because this is unlike a lot of, usually when you think of physical systems, it's rare to come across a product of two important parameters controlling each other, namely you multiply them by each other, right? And it turns out the physics doesn't care about the absolute number about those, as long as the multiple of them actually meet this minimum level on Earth.
And that was density and confinement time?
It's density and confinement time. So it's how many particles there are per unit volume, and then you multiply it by this characteristic time.
By how long you hold it together?
It's basically how long it holds its energy, technically, right? Okay, all very good. And so this is what confuses a lot of the public about fusion, because you'll see this picture. There's this great big magnet. Wow, they did fusion. Or you see this other thing, which is an electrode. They made fusion. Or you see this laser. They made fusion. What the heck do these things have to do with each other? What's happening is that they're using the same physical principle that I just talked about, but they're vastly changing the density and confinement time, basically about how you get to the multiple of those two. And so you can imagine what this is that if I allow the density to be very, very high, then I don't need a very long energy confinement time. And vice versa, if I make the density very low, I must get a high energy confinement time. And that's actually the approaches that are there. So just a quick comment, because this is why it is a little confused. If you look right now, the two methods of getting there that certainly have obtained the most publicity, but also probably the furthest along in terms of the scientific accomplishments, is in magnetic fusion, which is the focus of my work, which is, in that case, we use very, very low density fuel. The density of the particles in this is 100,000 times less than air. It's very, very undense. And this requires an energy confinement time of around 1 second, which doesn't seem very long, but recall what you're doing is, like, the particles that you're containing at 100 million degrees have such high average velocities that when they fuse, they would, like I'm here in Rhode Island right now, they would go from Rhode Island to Los Angeles in about 3 seconds. That's how fast they're going. So containing these kinds of things for a second is a pretty impressive feat indeed, right? And that's that approach. And this is the one. And how do we do this? We use the magnetic force to basically force those. And I can get back to more details and that, but just this comparison of that. Then I go to the other extreme of this. It's our colleagues that have performed this with lasers. And in the lasers are actually not heating the fuel, they're compressing the fuel. And they're achieving densities which are about 10 billion times higher than what we're using in magnetic fusion. And correspondingly, their energy confinement time is a fraction of a billionth of a second. And there are people and companies and other groups which are approaching things which exist in those in-between areas as well too, things like pinches and so forth. So this is one of the reasons for, it's an interesting one. It's both, I would argue, an advantage, but also has been one of the challenges of fusion. There's so many, because it turns out when you vary those physical parameters by so much, it actually vastly changes the technology that you're thinking about how you would actually get there. So this is an interesting thing thinking about how you develop it as an energy source, because you got a lot of choices, but there's so many choices. It's led to this. It's an interesting race in some sense, right? About how you would get there.
Right. So you can vary the density using various technologies, and you can vary the time to confinement using various technologies. Now, how exactly in your magnetic fusion designs, how exactly do you confine? Like, I'm trying to conceptualize this. you're using very, very powerful magnetic fields. I read that you've produced magnetic fields that are many multiples of the force of the entire Earth's magnetic field. Now I'm wondering, why doesn't that take a staggering amount of energy just to manage that? But also, how do you conceptualize the confinement space? Like, is it an enclosed magnetic field? And then inside that, there's this relatively low density hydrogen? And when does it become hydrogen plasma? And then if you're only confining it for a second, well, you don't want a power plant that only works for a second. So I don't see how to jump from that to something approximating a sustainable power source.
Yeah. So I'll parse that out. So first of all, so this is a focus on magnetic confinement. So the physical principle that's being used to contain the particles is another fundamental force called the Lorentz force, which is that if you have a charged particle that is in movement, and there's a magnetic field present, it will exert a force on that charged particle.
So it'll curve.
Yeah, well, it's actually so. This takes. I'm going to use my hands to try to get this. So magnetic fields. Most people know this from using a compass, and there's two things that are important about a magnetic field. Its amplitude, its magnitude, right? And it has a direction, because the way that we comment, it's a vector, right? So it has a direction. Okay. So I'm just going to tell you, I've got a magnetic field which is going like this, right? It's in this direction. It's pointed in this direction. And there's a certain amplitude to it. So what this means is when I put charged particles in the presence of this magnetic field, it exerts a force on it, which is an interesting force, by the way. It's a force that always acts in a direction that is orthogonal to the direction of the charged particle. When you work out the math of this, what this forces any particle to do, and like this, is that it will execute a circular orbit like this around the magnetic field. So no matter how fast it's going, it basically it's like it ties it to the magnetic field like that. And this is for both negative and charged particles. So remember the recollection of the definition of a plasma. So when it gets hot enough that most of the particles become charged, and that's certainly true in fusion plasmas. So every single individual particle is actually feeling a containment force, which is coming from that magnetic field. Okay, so what does that mean? So what that means is, and there's another special one, is that not only is it orthogonal to the direction of the charged particle, it's also must be orthogonal to the direction of the magnetic field itself. So what this means is that you can think of these as like barber poles of motion of the particles, that they're going along like this. They do not get affected in the direction that is along the magnetic field. So there is no containment along the magnetic field. So in general, what we do is we come up with a set of topologies of magnetic fields. Primarily, what we do is we make them close back on themselves, so there is no end to the magnetic field, right? And the way you do this is okay. So so in the end, you can think you had it right conceptually. It's basically, you can think of these vectors or line. We conceptualize them as lines of magnetic field and of magnetic force. And this basically, when it's put together in a particular configuration, it becomes extremely effective at holding this very hot fuel, because of that force it's exerting, because that circular motion doesn't allow them to escape unless some other thing happens, like they collide into another particle or something, which sets
is the strength of the magnetic field necessary proportionate to the average speed of the particles in question? So the higher the temperature, the higher the magnetic field required, the more powerful the magnetic field required?
So technically, the force that is exerted is proportional to the charge of the particle, but that doesn't matter, because that's fixed, because it's always the same. The velocity of the particle increases, the temperature increases. Its rate changes. It goes up as the square of the velocity, and it increases as the strength of the magnetic field as well.
Okay.
So in the end, what that ends up being in a practice, for fusion's sake, what this means is that in magnetic confinement has very critical consequences. Is that when you solve the particle's motion, in the end, what that means is that if you now consider I'm the magnetic field pointing like this, what we care about is the size of this orbit. the thing that's the size of this orbit, because it's basically a circular orbit. And if you keep everything else fixed and increase the strength of the magnetic field, the size of that orbit decreases. It shrinks because the force is better. So basically holds it closer to the magnetic field is what you want. And this is really important because it turns out from that other argument that although there are different arguments about this, is that the first argument about the requirement of the temperature, it turns out that there's a optimized temperature to access fusion. It's about 100 million degrees for the leading kind of fusion that we consider on Earth, which is not the same as it is. That's why it's a different temperature than the sun, because it's actually a different fuel combination that we use. It's the heavier forms of hydrogen. But anyway, that's at about 100 million degrees. So basically, anytime if you're a fusion power plant designer, you more or less always pick that temperature because it's the easiest one to achieve. And that means that the temperature is approximately fixed, and therefore the velocity is approximately fixed, and therefore in general, what you're controlling is the strength of the magnetic field to make that orbit smaller and smaller, and consequently make the engineering system that you have to build smaller.
Right. Does that also increase the density of the fuel?
It does, but for more subtle reasons. And it depends on it depends on the details of the shape of the magnetic bottle that you make. But in general, yes. But it's not so straightforward of a path to tell you about how it does it. But in general, the density of the fuel is allowed to increase, which is important because that actually means you can access then net energy gain. If you're at higher density, this allows you to do it at lower energy confinement time, which is a sort of a double win in the system, if you want to think of it that way.
So a couple of questions there. Go ahead.
Yeah. Well, and you had an important one about the 1 second business. So this is really important. So the 1 second is not the duration of the existence of the fuel. It's the characteristic time at which it holds energy. So namely this. So if you really think of it this way, it's almost like I think of, because it's the middle of winter right now, I'm thinking of heating our house and so forth. You can think of when I put a unit of energy into this house, there'll be some characteristic time, like a few hours, that'll basically like leak out right to the outside environment. But the house is still here all the time. That's more what we're doing. So this 1 second is that leakage time. It's not how long the house lasts. Yeah.
Starting a business can be tough, especially knowing how to run your online storefront. Thanks to Shopify, it's easier than ever. Shopify is the global commerce platform that helps you sell at every stage of your business. From the launch your online shop stage all the way to the did we just hit 1 million orders stage, Shopify's there to help you grow. Our marketing team uses Shopify every day to sell our merchandise, and we love how easy it is to add more items, ship products, and track conversions. Shopify helps you turn browsers into buyers with the internet's best converting checkout, up to 36% better compared to other leading commerce platforms. No matter how big you want to grow, Shopify gives you everything you need to take control and take your business to the next level. Sign up for a $1 per month trial period at shopify.com/JBP. Go to shopify.com/JBP now to grow your business no matter what stage you're at. That's shopify.com/JBP.
Okay. Now, you have to segregate the system from the ice-cold temperatures of terrestrial reality, let's say. How in the world then do you actually harness the heat that's thereby generated? How do you turn that into, transmissible energy or mechanical force?
Right. And there's a variety of ways to do it, but I'll walk through the system of how you do this. So I'll use magnetic confinement, and it varies a little bit if you use other containment schemes, but it's whatever, it's good. So in the end, basically, whatever you're doing to provide this force. So like the magnetic fields that we make use an electromagnet. This electromagnet is not in physical contact with this fuel at all, because the electromagnet makes a magnetic field at a distance. In fact, the leading way that we do this is we configure these magnetic fields, and in fact, the magnetic field can't even escape the magnets. It's just sort of encased inside of these. So usually you think of these as large circles or D shapes. You put these in a particular configuration, and on the inside, what you have is this, beautiful kind of magnetic cage, which is on the inside of it. So
Mhm.
the electromagnets have no idea there's like a star inside of them. And the star, all they're feeling is the magnetic field that's coming from the electromagnets. That's the key. It's physical isolation of the systems completely from one another, right? Because that's also confusing to everyone. It's like, so it's not a physical container in
Yeah,
that sense
yeah.
that's holding the fuel.
Right. It's like
Okay.
it's analogous in some ways to the gravitational field that keeps the Earth in orbit around the sun.
Exactly. It's an action at a distance. That's the right way to think of it,
Yeah.
right?
Yeah.
So it's doing it through that process. Right. So then this goes to well, what is fusion energy? Like where is the energy? That's the important
Yeah.
answer.
Yeah. And how do you get access to it?
Well, right. So the original energy source, as I said, is that the two particles collide and they actually make new particles. And by the nature of the fact that this is coming from the strong nuclear force, which is the thing that holds all nuclei together, the process, what that means is that the energy is actually in the kinetic energy or the velocity of the particles that result from this.
The
So
fused particles.
the fusion particles, yeah. So we take heavy forms of hydrogen, like deuterium, and fuse them together. And then what will come out? It's actually the same subatomic particles. The neutrons and protons, it's the same number that come out afterwards. They're just rearranged, right? So, for example, deuterium can come together, and then what you would have is something called you can have helium-3, which is two protons and one neutron, and then one spare neutron. Or you can rearrange it into another way that is actually it's a proton and a I'm losing track of it. It's a proton and a triton, which is a proton and two neutrons. So basically it's just rearrange them, and those have lower mass and they release energy. But because it interacts through that mechanism, it turns out the energy it's released in the kinetic energy of those particles that come flying up. And what happens is that it's when you write out the equations of the conservation equations, it's the lightest particles that the energy gets partitioned in a way that has to do with the masses of the things that result from this. And what happens?
And they can escape. They escape from the magnetic chamber.
It depends, actually. So some of them have electric charge, and some of them don't have electric charge. In particular, if it's a neutron, which is one of the fundamental particles, it has no electric charge, and therefore it can escape the medium immediately. It escapes the magnet because that has no electric charge. It feels no interaction with the other plasma particles, let alone the magnetic field, which it has no interaction with. So it escapes. So I'll use this one because it's the most prevalent approach right now is deuterium-tritium fusion. And what happens there is that those are the two heavy forms of hydrogen, and what is released is a helium, just a normal helium nucleus, and a neutron. So the helium has two protons, two neutrons, so it has a net charge in it. This cannot escape the magnetic bottle because it's feeling that force from the magnetic fields. Not say more important, but just as important, it is also feeling the electrostatic reactions, like you said, the magnets pushing against the poles pushing against each other. Well, it has electric charge just like all the other particles in it. So it has way more energy than the average energy of the particles that it's in. And now, therefore, it starts undergoing collision. So it's sort of like releasing like a cannonball. I think it's like a cannonball into one of those, those kiddie things where they have the big balls that they can go play in. It's like putting a cannonball into that. It's like it basically forces the cannonball to give its energy into all those other ones. That's what's happening. Because that's the heavy particle that has a mass of 4 units, because it's got two protons, two neutrons. And there's a total mass of 5 particles. It has the inverse of those, so it gets 1 out of 5. Sorry for the math, but that means it has 20% of the fusion energy is released. So that's very important because, like, where does that energy go? This is the heat. Remember, way back at the beginning of this, that in the end, fusion sustains itself by the fact that the particle energy, which is released by these single events, actually just ends up as being heat that is distributed amongst all the rest of the fuel. And this helium will not fuse again because it doesn't want to fuse because it's extremely stable. So it's basically the ash product of fusion. By the way, just a quick comment. Why fusion is that the process, the ash product of the thing that releases energy is helium, which is a harmless neutral gas, right? Wonderful. Unlike fission, where the thing that's made by the reaction itself is this soup or mix of just of hundreds of radioisotopes because you're splitting apart this really unstable uranium. So that's one of the other fundamental differences between fission.
Part of the cleanliness of the process and the simplicity in some sense of the process. Okay, so you have this increasingly hot plasma, and you explained the mechanisms there. How is that converted into usable electricity?
Yeah. So in some way you've got to get this back into heat. That's essentially how you're going to do it. So the two, I like to say it's this, fusion is basically two forms of recycling heat. So it's taking this major kinetic energy in these local particles and converting it into heat. So the first mechanism I just described, which is that heats the fuel itself. This is the key mechanism about how you make fusion a net energy source on Earth. It was that process that was solution to this thing with the product of the density. It's actually that process, because what it's telling you is that you're making enough fusion reactions that you're basically able to keep the system hot, because it's keeping itself hot. And that in this form of fusion, that's 20% of the energy. Very important. The 80% of the energy in that reaction is in a neutron. It cannot be contained, or it doesn't interact with this. So it interacts very weakly with matter because it doesn't have an electric charge. So what you have to do is put something in front of it. And what we tend to think of is either something, a liquid or a solid, that forces this neutron, which is like a cannonball, again, another cannonball going into this, and you force it to undergo interactions with the atoms that are in that solid or liquid phase. This thing we call a blanket, because you basically wrap the fusion thing around it. And the idea is that we force these neutrons, even though they escape the plasma and magnetic fields, they're forced to interact with this blanket. And after, it varies on the design, but after about 30 or 40 collisions, in general, they basically give up all their energy. And where is this energy? It's actually it's in the motion of the atoms that were in that blanket.
So that's like heating up water with it. Say, I don't know what you use in the blanket, but
yeah. So this is actually why fusion it's another reason why fusion is such an attractive energy source. This all sounds very exotic, but actually, if you just close your eyes and think, I give you a fusion power plant, what are you actually getting? You're getting a heat source. Because this blanket that heats up, you just get out this heat, and then you do whatever you use heat for. Make electricity, run industrial power plants, make synthetic fuels. It's really just it's adaptable to almost anything that you can imagine that we use from any other fundamental energy source. Yeah.
Right. Okay. So let's turn away from the engineering elements and the practicalities of the process to the practicalities of producing a usable energy source. So I've got two questions there, really. I know there's been we have reliable fission energy already, although some of the plants seem very complex. They're built as one-offs. There's tremendous bureaucratic red tape. There's a bit of a problem with nuclear waste. People are afraid of it. It's got a bad name. But I saw a company the other day, for example, I think I'm going to interview the CEO, that's produced this very cool little nuclear reactor that just sits on the back of a truck and that can be pulled to like a northern community. There's all these thorium salt reactors and so forth that have come on the market recently, and it looks like we're starting to mass produce them. And so, it seems to me, and I'm certainly ignorant about this, but it seems to me that if we had the political will, we could be turning to fission energy at a much higher scale than we have been. And so we have fission as a potential alternative, and the fusion problem is very interesting to solve technically. But why not devote our attention more particularly collectively to the fission issue? Why pursue fusion? And then if we're going to pursue fusion, where are we with fusion? Because I'm old enough now that, fusion has been 10 years in the future for 50 years. So what do you feel about all those issues?
Yeah, so get back to, to make it clear, I am personally totally in favor of deploying fission at a larger scale, to meet our energy security demands. It's actually, the reality is that fission is one of the, if not the safest forms of energy that we use right now. It's a great fit into the things that renewables are not. Renewables are a lot of great things, but they're not reliable because of their intermittency and their low power density. Fission is like that as well too. And as you commented too, it's like we've got a lot of experience with this, and we know that we can make it work. So I guess my comment too would be sort of a meta comment at first, which is the staggering challenge of, if we really are serious about decarbonization, which in my opinion as a society we are not yet serious about it, just based on the math of where we are. But if at some point, let's put it this way, we know mathematically sometime human civilization will run out of fossil fuels. We can argue about when it is, but it will, because it's a finite resource. And we need to think about what is a sustainable and deployable, almost universal, high energy density, dispatchable energy source. And our choices are so few that it's basically, it's not my argument about fission versus fission. It's just like, I want a set of alternatives on the table to let me do this, because this is the way almost all, I would argue all technologies work. We don't have monolithic solutions to these complex problems. They just don't really exist. And so my comment to this is that in many ways, I think the free market will decide this as well too, because there are just intrinsically different properties of fusion about its inherent safety, about the long-term consequences of the waste products that come out of fusion. The ability to license them is very different than fission. So while it has a commonality in some of the physics to fission, it's really such a different energy source, and there are so few other options in the long term. It's like, let's do this in some sense now, while we have the resources and the wherewithal to actually get after this problem.
Right. So you're not seeing them in competition in some sense at all. And your point
I
is
am
that
not, well, because fusions, the time scale is such that fission can be deployed now, right?
Yeah.
And we've got that. But there are serious look, any technology has consequences. Like if somebody comes and says, I've got a technology and it's got zero societal and environmental consequences, then go buy a bridge or something. It's like it doesn't exist. Okay, it just doesn't. And we know about these. Like we know about the consequences of fossil fuels, which have been, honestly, have been the reason that we get to live the way that we do now, by burning fossil fuels. But we also know there are direct health consequences. We can track these through, through air quality is a direct link actually to people, dying prematurely of asthma. Like we know these things, right? There's always a consequence to it. Anyway, so that's the meta view, I would say, is that you better get after these. And so what does it mean about a scalable energy source? And this is an interesting one, and about deploying it at a global level. Well, an interesting one that comes, and it's not a criticism of fission, but it's just the reality of it, is that because of the physical process that fission works on is actually at the heart of actually how you make a nuclear weapon, is that always has been linked to fission, is that you must have proliferation control. In fact, next week I'm going to be at a workshop that's discussing proliferation aspects of this. So you have to take this into account.
And you don't have that problem with fusion.
Well, it's a different problem in fusion. It's actually such a new technology. We're sort of figuring it out. In general, you don't, because in the end, you don't require uranium or plutonium to run a fusion device. So it's like it's very different from that. Okay, so that's that one. And also, and I think although people would argue that there are solutions to that, like the long-term waste storage one is an interesting one. Is that because in fission, this is linked to the physical process really of the fission itself. In fusion, the physical process doesn't actually make any radioactive waste, it makes helium. But the engineering that you put around this, like what you make this blanket out of and what you do these other things, these are engineering and design choices that you have about improving the public acceptance and the viability, the licensability of the fusion one. It's an engineering choice that you have, even though there's some pretty severe challenges around making that engineering work. So that's where I would comment to that. And in the end, the fact, and I should get back to this one, is that it is like they call it, we have to watch out how you use analogies, but the holy grail of fusion of energy, the things in this. Why? It's because it actually uses very few raw materials to build the thing, if you build it effectively, and the fundamental fuel source is essentially inexhaustible on Earth and freely available to everyone. It's like that's why you pursue it, right? But it's important to understand what it is that you're pursuing, which I think was your second question. Yes.
No matter where you're listening, no matter what job you have, the clothes you wear to work say a lot about you. It's time to take your style to the next level. With Mizzen & Main dress shirts, you don't have to sacrifice comfort for style. Their performance fabric dress shirts feel just as good as they look. Mizzen & Main invented the performance fabric dress shirt 10 years ago, and they've practically perfected it. It's lightweight, breathable, moisture-wicking, wrinkle-resistant, and the most comfortable shirt on the market. You can wear their clothes to work, throw them in a suitcase, or keep them by your at-home desk for when you need to look sharp for an interview. Whatever you do and wherever you wear it, know that you'll look and feel amazing. So whether you're attending an important meeting or a networking event, or simply want to impress your colleagues, Mizzen & Main has everything you need. So what are you waiting for? Spruce up your style with Mizzen & Main. Go to mizzenandmain.com and use code Jordan to get 25% off any purchase of $130 or more. That's MIZZEN and main.com, promo code Jordan for 25% off today.
Right. Well, I'd like to take the skeptical approach to that now, because as I said, this has been for now. Look, I mean, we haven't really been trying to develop fusion technologies for very long. If you think on any reasonable time scale of technological advancement, I mean, we're so accustomed to having complex technological problems solved within the spans of single lifetimes that we think anything that takes 200 years is hopeless. And so I'm certainly not making the case that fusion is an uncrackable problem. But having said that, it has been continually announced for many decades that, fusion is a decade into the future, viable fusion, and that would be fusion, as you pointed out, that produces more energy than it takes to produce. And so now you've been involved in until recently headed very thorough project developing this magnetic technology that we described. You stepped down from that position in November, if I have my facts straight. So tell us about that project. Tell us where you think we are on the fusion horizon, and what you think the next steps and something approximating a timeline might be. And maybe you could also tell us why we might be optimistic about that timeline.
Yeah, right. Again, the meta comment is, it's interesting on AI, right? The term artificial intelligence was invented in the 1970s, which is fittingly about the same time that fusion technology really started taking off as well too, right? Or maybe it's even the 60s, like Marvin Minsky and so anyway. These ideas are around because they survive because they're compelling ideas, is my argument. And then all of a sudden things happen that all of a sudden makes this thing that people conceive of, I get the dream of this, right? And all of a sudden things happen that all of a sudden make it, a reality, you see something right around them. So I'll pull back. That's the meta comment. Why fusion, right? So some of it is the pull, right? That I would argue that as a society, if we really are serious about decarbonizing, the set of choices we have in front of us about replacing 82% of our fundamental energy, which comes from fossil fuels and basically hasn't changed in decades. You need just massive amounts of carbon-free energy, massive amounts. So that pull that is coming from that has increased significantly compared to like the 90s or something like 1990s. Very important. I think it's actually not, and it's even more nuanced than that. It's not just access to that kind of energy. It's like the realization that renewables alone, because of their intrinsic limitations, like try to run a gigawatt, chemical processing plant on renewables. It's like
especially when it's cold.
Oh yeah. Well, I mean, the science doesn't. The science is against it. It's not nothing against renewable. You just have to be cognizant of the limitations of any kind of energy source. It's like the limitation in fusion, by the way. Like you can't make a fusion power plant that heats this home because everything's got to be at bigger scale. It has to make way more power than would be appropriate for heating this home. Everything's got limitations. Surround on those. So I think this was part of it. And then, of course, what happens, like in a lot of fusion. This distinguishes it. The science I described has been known for a long time, and the criteria to make fusion have been known for a long time. So what happens is the reality of actually making fusion practical, as usual, it comes from synergies of technological and scientific advances that tend to make you feel that it's ready for prime time. And I'll comment on this, is that really in the last 10 years, there's been I think, a set of those. One of them has been computational power. It's a really complex problem. One of the origins of the company that we launched out of MIT and some of the ideas that we've been pursuing came out of my classroom. Why I say this, it's like the computational power that's available to my students in a single semester class at MIT surpasses the computational power available to people one generation ago that were actually trying to design the biggest fusion experiment in the world. It's like, that's going to make a difference, right? And because it's a complex problem. I think the other part is because fusion's advance seemed to take a hiatus because we were trying to figure out the way past that next threshold, particularly of the scientific threshold was getting net energy, which meant that what that means is that when you hit that, you're actually the fusion reactions are the dominant heat source in it, and there are multiple approaches to that, and it was a big step, and we needed to get our scientific feet underneath us, and that was honestly like a 2-decade process. I was heavily involved personally in that as well too. It's a major scientific task to basically get after these things, and that particularly evoked itself in forms of advanced magnetic confinement devices, one called ITER, which is in the south of France, and now our own experiment, that's been launched out of MIT and Commonwealth Fusion Systems, and also with the laser fusion, which had a big breakthrough approximately a year ago as well too. And guess what? Like one of them did break through, right? The laser experiment got to the point where they got the fuel to the place where the fusion reactions were the dominant heat source. An amazing scientific accomplishment. And this was the thing that sort of broke through the news cycle, if you remember, in December of 22. Yeah, very, very important. And of course, everybody looked at it. It's like everybody, calm down about an energy source next week, but a major scientific accomplishment. And this is the fruit of decades of work, right? That the general public won't see. So that's the second one. Like we really know a lot more than we did 20 years ago through that and through computation. And the computation, by the way, affects the science and the engineering. They're sort of the synergistic buildup.
Right.
And then the final one was advances in technologies that come from places that weren't necessarily in fusion. And that's one of the ones that we discovered, was that namely, there was a commercialization of a new kind of technology, a new kind of superconductor material that was going to apparently allow us to greatly improve the efficiency of the magnetic bottle that we were making in that approach. And interestingly, like the path of that one came from a fundamental science discovery in the late 1980s, won the Nobel Prize in Physics. Everybody went crazy because this is so-called superconductor, which could say superconducting at extraordinarily, for that kind of technology, high temperatures. Usually superconductors are near absolute zero. This is at a stunning like 70 degrees above absolute zero, remains superconducting. But that took, over 20 years to commercialize. And it turns out our team was ready, sort of with the right set of ideas, to take that new material now in a commercial form and in terms of a tape, and in turns it turned it into into a highly performing electromagnet that produces this cage. And that's in fact was a major pursuit of my group at MIT, and now the commercialization aspect of this with Commonwealth Fusion Systems, which a couple of years ago essentially demonstrated this quantum jump in the capability of the magnet to be an effective container for the fuel. And just to put that one in context, is that was approximately a factor of 20 to 40 improvement in the efficiency of this. So this meant that the cost of being able to build a device that would see fusion, this net energy gain for the first time, it shrunk it by a factor of approximately 30 to 40. So that's an enormous one, which goes. So, but by the way, then, and now there are other fusion concepts which can also use that breakthrough along with the computing power to design it. In fact, early this morning, I was having a conversation with my MIT colleagues about how we might apply this to a different configuration. All this being said is that it's a lot of details I know to go through. Look at technology breakthroughs. They always happen this way. That namely, there's things which are sitting there which are ideas but are hard to imagine self-consistently together as a commercial product or something that we can all use. And then what happens is a couple of things pop together, and all of a sudden what seemed impossible becomes, I'm not going to say inevitable, I'd never say inevitable because that's too much hubris, but I think it becomes much more likely actually around on this. And of course, the important thing for this is that is there a customer on the other side if you're thinking about commercialization? And the argument here is that in the energy world, we've become hungrier and hungrier for these kinds of products, not less hungry for those. So, and that, I think that's why the landscape has changed for fusion.
Okay. So you're pointing to clear advances on the laser side, advances in material technology, stunning advances in computational ability, which I presume enables you to model the things that you would otherwise have to build and test much more precisely, much more rapidly. And so you can see an acceleration of movement towards the end goal. How far away do you think, maybe this is an unfair question, and if it is, well, deal with it however you want, but how far away do you feel that the teams that you've been leading or the team that you've been leading is away on the magnetic containment side from producing a reaction that produces more energy than it consumes? I mean, you talked about commercializing this, and I know there are plans in the work for that, so I presume you feel that you're on the threshold of this or close to it. How do you know that, and how do you track your progress and predict?
Yeah, so one of them is that there's a place about an hour drive away from here in suburban Boston that has built the buildings in which it will be in, that has built the factory that is building the magnets, which basically took the magnet development that we did jointly with the company at MIT, between MIT and the company, and they're building the magnets. In fact, I'm on this podcast, I'm missing my weekly meeting about the magnet fabrication. Okay, that because that's how real it is. The money is there, the team is there, it's putting it together. And right now the projection is it's a few years away, like a couple of years away. I can't speak in detail about schedules, but that's okay. So that kind of puts this into context. And what do we mean by it, right? It is something that makes fusion at a commercially relevant scale, namely that it's in the orders of hundreds of millions of watts of fusion power, and it has a net energy gain in the plasma, which is a fundamental requirement, obviously, to make a net energy system around on that. Right. So in some sense, I would ask you as somebody who obviously you're scientifically literate but not an expert in fusion. If you see something like that, do you think fusion is taking a big step towards commercialization?
Right. Well, what you see is that people are willing to bet resources they actually have at hand on that realization. And so you'd assume, if they're sensible people, and I suspect they are, that they've done their due diligence and believe that this is a possibility in some time frame that makes the investment worthwhile, and that they're more interested in that than they would be investing in fission, for example, which is a more proven technology. So that's how it looks from the outside. I have two issues that came up in our discussion that I didn't get quite cleared up that I'd like to return to, and then we can move the discussion forward more generally again. When the plasma forms and the electrons are stripped off the hydrogen plasma, what happens to the electrons?
The electrons are contained as well too. So a fundamental feature of the plasma is essentially an equal set of negative and positive charged particles. That's actually one of the definitions of the plasma.
Really? I see. So they're in the soup.
They're in the soup. Yeah. Which is interesting because they do not fuse together. They're fundamental particles that do not change. And in fact, they're an interesting one because it's a good, if you mind, I'll just divert this because it's an interesting technical challenge if you think of it this way, is that the electrons have way less mass than the other part. They're 2,000 times less massive than than the other parts. So this is a weird fluid. It's one of the reasons why why plasma physics is complex. Because you have a fluid where the two particles have a difference of mass of an inertia of a factor of 2,000 from each other.
Right.
So they can behave quite differently. So for example, the size of that orbit that I mentioned, it's inherently 100 times smaller for the electrons than it is for the other particles, which means this is why it's a difficult physics problem because you're dealing across very different spatial scales because of that.
Okay.
But it's interesting in an earthly fusion system, these are really important. Why is this? Because you've got this equal ensemble of the hydrogen species, the nuclei, and the electrons. They're all together like this. They're actually exchanging energy to each other through collisions as well too. But when the fusion reaction occurs, this particle that is ejected is so energetic that it's actually going, even though it has a mass which is way more than the electrons, it's actually going at a velocity which is actually about the same as the electrons because it's got so much pop to it. And through reasons I won't derive, this means that actually that very fast particle technically gives most of its energy into the electrons, not into the rest of the fuel. So the electrons get hot, and then the electrons actually exchange energy through collisions with the fuel, and then it's the fuel that makes the fusion. But the rate of fusion fuel actually is a thing that sets the rate at which those energetic particles go out and hit the electrons. Wow! So you see the physical coupling in this is complex because there's essentially three independent species sort of navigating this with each other through collisions and power balance. This is just one of the kinds of complexities that we deal with in fusion systems. Yeah.
So thank you for answering that. I had a question too on the conceptualization side of this with regards to the justification for fusion technology. Now you justified it, and I'm not putting words in your mouth, and I hope not to, but one of the angles of justification that you adopted was an emphasis on decarbonization. But it seems to me that the proponents of fusion power have a better environmental sustainability argument than decarbonization. So, for example, we know that there's almost nothing more tightly tied to economic progression and success, the amelioration of absolute poverty, than decreased energy cost. I mean, it's almost a one-to-one relationship because energy is work and work is productivity and productivity is wealth. And so that's not much of a complex causal scheme. It also turns out that if you get the average GDP of the absolutely poverty-stricken up to about $5,000 per year, they start taking a long-term view of environmental sustainability at the local level. Because instead of having to scrabble for their lunch in the dirt and burn dung, they can start thinking about what sort of greenery might be around for their children, right? And so it seems to me that instead of following the green pathway, so to speak, and pointing to the utility of fusion energy as a substitute for fossil fuels, which in principle might become more expensive as they become more scarce, and which also could be used perhaps more wisely for the production of chemicals rather than to burn.
Exactly, because it's a rootstock, right? Yes.
Well,
yeah,
absolutely,
limited, yes.
and absolutely, and for fertilizer as well. Let's say that beating the drum for driving the cost of energy down to the lowest possible level conceivable seems to me to be a more appropriate and potentially deeper long-term, say, public relations strategy. Like, what could we do with the world if we had an inexhaustible source of inexpensive energy? I mean, it makes enterprises like desalinization, for example, widely possible. And well, that would be a wonderful thing, given that in principle, we're going to be facing water shortages in the future as well. So I'm wondering, what's your view with regards to the viability of fusion as a genuinely inexpensive and universally available source, apart from the fact of its cleanliness and safety, which is obviously relevant?
Yeah. Right. So that is actually the challenge, I would argue, in front of us as technologists who propose fusion energy systems, right? Is that I feel, my belief is that we've gotten past the point where we're because we've demonstrated so many of the different parts of the system, like the science of it, while it sounds like science fiction, has actually been done. By the way, for example, 100 million degrees, which sounds like science fiction. We ran an experiment on the campus of MIT where when we ran the experiment 30 times a day for a few seconds at a time, we'd make the fuel 100 million degrees. Like this. I remember we had a VIP visitor who saw one of these, and they said, "Why isn't everybody applauding?" Because we do it. We did it 30 times a day. The scientific viability is there. And what was missing were two components, I would argue. So one was, were you past the point where you felt like when the system became more self-determined and heating itself, that it was going to be, everything was going to behave, properly? And it's not all the way obviously there, but the laser fusion result has been a major impetus to us saying that, darn it, that looks pretty good. And the project that called Spark, which is the one which is outside of Boston, basically that shows it for magnetic fusion, and also shows the fusion power at a commercial type of scale. It's like, I think your question about essentially the physical reality of fusion fades away. And what becomes the question now is, what price point can you deliver the energy system at?
Right.
And as you heard from, because all the exotic parts of this containment and all this, it's like, of course that's still important, but now it comes to the effectiveness of the integrated engineering system that you're building, this so-called blanket. Like, how effectively do you extract the heat? It sounds like simple things, but it's not. Like, what temperature do you extract the heat at? This is enormously important in terms of the thermodynamic efficiency, what you might use the power for. How reliable are those systems? Because they're in a pretty intense environment, right? So how reliable are the components inside of them? How long will it last? These are the things, and that's why, although some of my colleagues still disagree with this, I feel the fusion technology, the fusion development world has changed in the last few years, is that we're starting to ask the question of what will the cost be, not whether or not can we do it, right? And and I think
that's a good deal. Well,
so this is very, but it's still hard, by the way. I mean, because
right.
It varies across all these different approaches about how you might. And the cool thing is that there's 30 some things, at huge varieties of scientific, maturity and so forth, that are trying to answer that question. Because in the end, what answers that question about the is the marketplace, right?
Right.
is that's what's going to do it. In fact, we're doing a study of this at MIT right now, which is we're calculating with understanding and some projections of energy markets, like where will that be? So that namely, all new energy sources tend to penetrate at some more expensive some point, because people are saying, well, it's okay because it's a new energy source, will kind of give you a break. But if you want to deploy it at mass scale, you got to get it competitive to the other ones. And then you sort of look at the relative advantages and disadvantages. So that's exactly where we should go. And I think the simple answer is, if you get fusion in the right ballpark and enter it and start reducing the price of it, it's incredibly disruptive to the energy.
Right.
It's right, of course, because it's so expandable. That's one of the. And in the end, the physics or the science of the energy source does matter, right? And in the end, you cannot physically increase the solar radiant heat flux on the surface of the Earth. It's fixed, right? And you can't snap your fingers and make the wind intensity higher or things like that. And all these different things, this is why we pursued fusion, is that if you look at the ideal of fusion is you can't run out of the resources, apparently, as far as we can tell, about deploying this, right? And so that end goal is that it's like, if it becomes inexpensive and you can deploy it at fast timescales, it becomes a dominant energy source. This is why people want to invest in it, because it's not just altruism. It's like, this is a business proposition. But we've got this serious challenge of that it's still we've only turned that corner in the last few years. And what this means is that we're facing the challenge of, how do you take these different concepts and actually deliver on the full integrated energy product? We've got a long ways to go on that.
Well, we have, on the optimistic side, we have quite a world waiting for us if we're sensible and fortunate. I mean, you can imagine here. So I know a group of people who are avidly pursuing atomic level deposition in 3D printing, which opens up the possibility that we'll literally be able to print anything we can model, and then at scale, and then very inexpensively. And so just God only knows what that's going to produce. And these aren't pie in the sky technologies. These sorts of printers already exist, and they're working very hard on making them economically viable and distributable and dirt cheap as well, eventually. And so that's remarkable. And then we have these AI systems that are now conversation level, that I can envision being put into technologies that will be able to teach every child on earth every single subject there is at their level of comprehension, and also exceedingly inexpensively. And then with this, if this...
Can I just give an anecdote to that, actually?
Sure.
Because we're both professors, or have been professors, and it's I recall my colleagues, when Chat GPT came out, they were rapidly using, they were checking to see, well, how would students like cheat, basically, using GPT, and done and they're putting qualifying exam questions and so forth. And like, my comment to them was, you might be not realizing whose job this might imperil.
Yeah, no kidding.
Right? What does this mean? But by the way, it's like, as usual with these big disruptive ones, which I think fusion would be as well too, people probably look at it a little bit incorrectly, is that by the way, I'm sorry for the sideline, but one of the greatest challenges we have right now in fusion is people. And it's because this transition from a science-only program to thinking about integrated engineering energy products happens so fast. In fact, I just wrote a paper. In fact, I'm giving a seminar, national webinar on Friday about it. It's like, our academic system is just like, because it's frozen in that place that it was, 50, like academic systems are, right? They tend to have really long lag times and lead times. It's like, oh my gosh, it's like, we are not ready for this at all. So in fact, we don't even have the right distributions of kinds of expertise and faculty and so forth. It's like, oh, well, what if in fact I, and there's set up, what if I can, because I would argue my specialties is integrated fusion design analysis, and that's one of my classes. I get to teach, order 15 to 20 students every 1 or 2 years at MIT. What if I can teach thousands of students of that through AI? Like,
right, absolutely.
Right? And so the synergies in this are amazing. The other part, which is, in fact, we just signed an agreement with the International Atomic Energy Agency that we are active and very, very actively pursuing AI use to basically be the entity that runs the power plant.
Oh yes.
Of course, right?
And are the AI systems helping you now already with design?
It was almost ready for it, and I almost thought about using it in my design course that's coming up actually in a few weeks. It wasn't quite ready for prime time for that. But here's, of course, what the amazing thing about being at a university, by the way, the students had already started to do this. And so what did they do is, I told you we ran this experiment. It was an integrated fusion experiment, had electromagnets in it. It made this magnetic cage, had the 100 million degree fuel, had this amazing set of measurement tools and so forth. But it also had people running it, so all that data is, of course, recorded and used. But it also had people, experts, who were examining the data and inferring things about the performance of the fuel and so forth. But that was sitting there as essentially as a static, not really useful set of dialogues that had happened in that. they're training an AI language format, basically on sort of 20 plus years of human expertise built now into AI thing. It's just like, oh my gosh, so this is what I also find so cool about being a technologist, by the way. It's always these synergies of things that apply to each other, like these new superconductors and a new kind of magnet, then a new kind of AI, then a new kind of thing, and then you just keep bootstrapping yourself up all the way to the technological ladder. I think it's
well, you're at a point now where if there was enough of your published and spoken material, is that you can have a dialogue with yourself about problems you haven't solved. So I'll give you an example. We built an AI system recently based on the first part of a book that I'm writing. And the book is an analysis of deep themes in biblical stories. So you could imagine that your bright students are going to put together all the relevant literature that pertains to your engineering problems. And at least you'll have a partner that'll be something like an instantiation of you that you could, or you and your colleagues, that you could discuss these problems with.
Yeah, even better that it's an accumulative one of those, right? And I've been at Fusion now for 30 some years, a faculty member. It's like I can tell you almost all of my insightful breakthroughs came with a version of that, which is that we already had this. It's called training students at a university.
Yeah, right, exactly.
Like why do we have universities? One of the reasons is we accumulate people in the same place, and we take senior people who convey certain aspects of basic knowledge and so forth, which are required to make sense of the problem. But it's like, I'm like almost every innovation that has ever come has been sitting there talking with the student of explaining about why such and such a thing is a problem. And they go, and they ask some, quote unquote, stupid questions. Not stupid at all. It's actually an insightful question, because in some sense they're training their own neural network, right?
Yeah, right.
Around these
Definitely.
things. And then all of a sudden you sort of see it from a different angle, or you take it from a different approach. It's been almost all the totality of my innovations in the last 25 years have been almost all through student interactions. So it's another version of that, I think, is what I'd be saying. Yeah. So those are the kinds of and by the way, that is another one where you talked about. In fact, I left that off. I should have reminded myself of that one, which is additive manufacturing is another one of those aspects that is coming to bear in Fusion, because in the end we build these complex physical objects. The ability to design it from the ground up is just,
and to produce variants rapidly.
Oh my gosh, yeah. A simple example is, in the end, while you got this containment system, there has to be this really effective, essentially heat exchanger on the outside of this to remove this kinetic and get it into a usable heat form. The way I would describe this to date is we build, because we could build it this way. You build square blocks of things and you put a round hole in it and you pass, some fluid through it to get it to cool. Nature never cools anything that way. Take a look at a leaf, right? But additive manufacturing allows us to make the equivalents of leaves, or like the capillary systems in our own bodies. It's like, what that means, we don't even know.
Right, even at the atomic scale.
And then to do it at the atomic scale, which means you can start mimicking biological functions as well, too. Amazing. Yeah, it's almost like a science fiction world that we live in. It's amazing that people sort of comment that it's like again, sort of medical, that are pessimistic about where we're going. If you'd have shown me when I was a young boy in rural Saskatchewan, if you would have shown me this technology, I would have thought I was living in a movie.
Right, absolutely. Yeah. And it's a new movie every day at the moment. Well, that was great, man. I really appreciate, first of all, stepping us through the complex technical elements of understanding the fusion technology, which I think we managed very well, and then moving effectively from that into the practical realization and the problems at hand, and also interleaving with that, a sense of, I would say it's like 1950s to 1970s can-do engineering optimism, something I really loved about engineers in general, about MIT in particular. Certainly saw that at Stanford too, and with the Silicon Valley types, is that there isn't a problem that we can't crack. And it's lovely to see that spirit still alive at MIT. For everyone watching and listening, I'm going to continue this conversation, as I always do, on the Daily Wire Plus side. It turns out that Dr. Whyte and I have some autobiographical features in common because he grew up like I did in Western Canada. And so I'm going to harass him about that and see how he emerged from that Canadian prairie environment into a position of foremost influence at MIT. We're going to talk too about how his interest in fusion technology, in engineering and in physics developed. And so, as some of you watching and listening know, I'm very interested in how people find their purpose, find their meaning, and the interweaved relationship between the demands of their conscience, right? The problems they're trying to solve that lay themselves in front of them as objects for them to take responsibility for, and then the spontaneous interest that manifests itself to people around topics that, aren't, it's a very curious thing how interest finds its home. As a Saskatchewan prairie boy, you got obsessed with fusion technology. It's like, well, why? Well, that's what we're going to delve into on the Daily Wire Plus side. So you guys who are watching and listening can join us there if you're inclined to. In the meantime, thank you very much, Dr. Whyte, for walking us through all that and for agreeing to be a guest on my show. Congratulations on the success that you've had. We'll be watching to see how this unfolds over the next few years, including the success of this commercial enterprise, because it's an exciting possibility that's making itself manifest. And so, and to everybody watching and listening in the Daily Wire Plus crew, thank you very much for your time and attention. Good getting to know you a bit, and thanks again.
Thanks for the opportunity. Appreciated it.